Welcome to a new test and teardown video. This time it's a Wavetek programmable signal source model 172B. I think this unit is from about 1981. The one I got here is with option 1 and 2. One of them means it's the front. So this entire front here is an option actually, with the displays and all the little push buttons here and all that stuff. That is actually an option. You can buy this signal generator without the front. I found one for sale on eBay for $3,950. And I don't know what he's been drinking. Definitely something with high octane, because I got this one for free from one of my super nice and friendly sponsors. I don't even know if it works or anything. Oh yeah, this is a 19-inch unit, of course. It is 60 centimeters deep from here, plus 6 centimeters more up here, so 66 centimeter deep. So I mean, this is my knee. It's that crazy. And the weight is 24.4 kilos. I will now lift it up on the table and have a look inside. I did, of course, deep clean it, and I put a tiny little drop of white paint into some of the little scratches to make it look real pretty on those pictures here. So look at that. Rear of the unit, we got a little bit of funny connectors here. ASCII data input. Oh, nothing is connected. Options. Okay, we've got tons of option possibilities and different reference in and out. Okay, that is of course the address. There's another little thing that worries me a little bit. This one says bottom, but this is the top. So somebody's been poking around with this one and just assembled it real fast. Why are they marked like that? And it was safety tested in 2002. No, this is the next safety testing. And so then this is written in German. So that means it was imported. Oh no. And this is, of course, sometimes I just say this big oh no when I open stuff. But remember, I get stuff that is a broken defect, or somebody gave it up, or somebody don't have time or money to invest and fix it. So there's not a big thing. I mean, don't cry when you get stuff that doesn't work, right? But look here. Look how bent that circuit board is. I think it's difficult to photo this. Something really, really bad happened here. Everything here is bent quite a lot. So how is this possible? I should probably unscrew. I think those brackets hold the boards somehow. So I need to unscrew these and then lift up, and then I can pull all the boards. But this is the main design of this unit. We got some transformers here at the back. The funny thing is they look really different. So this is maybe an isolation transformer, an extra isolation, something. Let's figure that out later. But at least we got the power supply. Everything is plug-in boards just to a main bottom board here. I don't think this motherboard does anything other than just connecting everything together. And that will be the front, which is an option. And you can just pull everything here except for the switch, and then there should be another blank front installed. So I think it's just really, really beautiful the way it's designed. It looks fantastic. I mean, look how service friendly this is. You just unscrew a transistor and bend up one pin at a time for desoldering and easy access one by one. There's no extra things you need to work with. I mean, this should be like a school example how you should design stuff for easy service friendliness when it comes to regulators, heat sinks, circuit board and transistors to circuit board mountings and everything like that. I mean, just see those pictures and you get the idea of service friendliness. This is what we want to see, everybody. Wow, I am so impressed. Super nice and beautiful layout as well. This is a 2-layer board. This connector here is probably main entry from some rectifiers that's probably also located here at the back or something like that. I haven't yet found them. This is a little thermal switch. Maybe that is what they refer to danger high voltage. So that little connector here is quite close. Maybe it was no, okay. Probably mains voltage goes through this one, and if the heatsink is red, glowing, melting, something broken, somewhere shorted, whatever, it should disconnect mains. Yes, of course, everything here is, I don't know, it's really difficult to photo. And it doesn't really look that bad here. I could probably bend this back. I haven't yet figured out why it was this really bad. Probably the distance between this and that little groove here is maybe too small. Maybe they're welded to the case. Oh no, we got a screw down here. And this is the screw for the case. I don't know how. Maybe there's something here that moved, but it also reveals this, right? Well, I better take out some more modules and inspect a little bit more. So that is they call this the pass transistor board. This is obviously all the power supplies, and this one right next to it is of course the power supply that measures, regulate and handle all the different power supplies. So we got all the test points for the different voltages. It says here, so we got plus minus 24 and plus minus 5. Oh yeah, plus minus 15 and a positive 12. Quite a lot of different voltages. Yeah, not a lot to say about this board, but I will just keep pulling out boards and investigate next 3 modules. This one is called memory RAM. Look at those. Super cool chips in 1981. Test numbering on chips. Oh, from 86. So I found something that I found a little bit weird. What is that? Scratchy, weird mark right there. So this I need to look a little bit more. And then maybe this one is the digital brain. It's just called digital. But we got this one. Doesn't really look like something fancy. This is a well, I actually don't really know, but this is called a digital board. Where's the crystal and where's everything? Oh, Is that for clock isolation or some stuff? Then we got memory. This is probably the program memory, so that will be read-only memory. Where is that? It says not a lot. But you can upgrade this with a lot more memory chips. Just 2 little 8-bit EEPROMs. One here was halfway out of the socket. And here we got a little crystal. And some... Oh, I actually don't know what that one is. From 87, I bet. Oh, look at that. The layout is definitely made with tape on film. Manual work, all of that before CAD. See the different angles and shapes of tracks. What is that? Is that a little via come loose? The distances here is not super good isolation and safety distances. It really looks like shorts. But they could have, you know, used more space here, moved everything down here, and just moved and used all this space. Look at the funny way the tracks go here, and that is because we had something there, probably some capacitors or some connections, and that reveals the space you got here. Because with a manual layout, you don't just pull the tracks back. I totally love it. The next 2 boards. The first one, I believe, is a DA converter. And a little analog multiplexer, some op amps, transistor drive, power drive. And that will be the output connector. I don't know exactly what is inside this big box, but it looks interesting, so I will get back to that one when I'm done my inspection round of all the different boards. We can of course have a little look here what it says. Yeah, I believe that will be the 80. It has to be, right? So the output goes to this board here, and this is called a 3-digit attenuator assembly. So look at all those relays doing all the different attenuations, and then this one goes here, and then there is another connector somewhere. Ah, it was here on the back of that one, and it's connected here to that one, right? And this one is called output. So there's also, yes, of course, this is my main output from that one. So there's another power amplifier or something inside this one. But then, why is it going back and forward with only one wire? How is that even possible? I don't understand that. Well. Function preamp. Well, this looks quite boring. Just a few relays. A little bit of analog multiplexers, transistors, and some adjustments for zero and sine wave and peak, this and that. Not a lot of cool things to see here. Yeah, they replaced some relays. This one looks, however, really interesting. I do not know what that one is yet, but I am going to find out. So we got some symmetry, zero adjustments. We got some really nice capacitors. And this box here is really going to be cool. I look forward to open that one. See the little screws? And they are made of plastic. And somehow it's important to isolate and shield individually those 2 compartments. And then we got a little gasket, something here at the at the top and adjustments here and here and here. Maybe this has something to do with crystal oscillators or clock generators and multipliers and all that kind of stuff, because this looks very interesting to me, at least. So that will be the next one. And there isn't any text that explains what exactly this one is doing. I see a lot of digital ICs and a little bit of analog ICs, tons of trimmers for gain adjustments, stuff like that. We've got a lot of op amps, and maybe a little analog to digital converter. Yeah, that's basically what this module is about. I don't really see anything super fancy here. Let's look a little bit at the last three modules. They use the same shield, and of course they do. Why design and manufacture three individual shields? So I need to unscrew those so we can have a little look. So this will be the last three modules, and I removed the shielding. And I believe those three makes up all the different frequency generations we need in this unit. See, we got mixer and loops and divider logic, VCO buffers, output mixers, input mixer, whatever buffer here. I mean, this is they call this a digit 1 mixer for clock generation, obviously, but I'm not able to go inside this one, just bad luck. Of course, it's VCOs and phase detection and all that kind of stuff to... Ooh, look at that one. It's the N82S23 something, right? So that will be one of those proms, one-time programmables, and there's a little number here on them. I believe this is 8-bit of data in a tiny little package. So they're really, really fast. And of course they use them to address all the different digital circuits. So you'll probably also find these in some of the other boards to handle address selection and all that kind of stuff. The next one here looks a lot like it again. We got some, I think this is the 60 megahertz. Looks a lot like filters, amplifiers, PLLs, and little mixers, amplifiers. Here's another mixer. So digital interface, divider logic, amplifiers, loop filters. Yeah, all sorts of really, really beautiful things. And the last one is my... Oops, be careful, is my main oscillator, main reference oscillator. And it's not even temperature control, temperature anything really. There's a little varactor, capacitor, diode right there in the oscillator system, so you can remote control and PLL it and all that kind of stuff. And then it's multiplied and then doubled to 60. And that is, oh, there's also a 40 megahertz VCO. Yes, that's right. Loop filters, difference frequency and logic for all that. Yeah, a lot of hardware needed to handle all the different clocks. So this is, of course, the reference board. I also want to go a little bit back to the power supply and the regulator, the transistor board. I started by showing and telling how happy I am about the easy service friendliness of this design, and it is definitely a brilliant service friendly design. But there is a big error in this design, and of course I realized this after the video, and you can see the problem here is the straight pins of all the transistors. That means when things get warm and cold, every time you power stuff up, and when things mechanically expand and all those kinds of things, you will end pulling differently on those pins and all that kind of stuff. So this is a wrong mounting style. The idea is you should actually bend the pins of your transistors to the circuit board a little bit so you would handle thermal expansion. And I made it here on one of them just to show my point. Maybe I did it a little bit too much. Over exaggeration is a good way to prove a point, but that is how I would have done it. Of course, you need to hold real firmly down here with a tool so you don't bend the pins when they are coming outside of this plastic package. You definitely don't want to do that, but this is definitely how I would recommend doing it in amplifiers and audio equipment. Everywhere you service things and everywhere you mount anything like that, power transistors or regulators or whatever, think about thermal expansion, and you don't want high forces to be in your solder joints. Earlier I promised to open this one with the circuit board shield. It's a little bit funny with it. It looks like we got two different. Aha, that is just the little rubber thingies. That is what's causing it. It's just completely random luck. They placed them a little bit like that. So that was not what I thought it would be. But look at the circuit boards in here. They're not even touching the metal. They're sitting in here in each little compartment, shielded from each other. Super nice and beautifully constructed. That is definitely something. But there is another little problem here. I don't know if you see the corrosion up here. It's completely corroded. Somehow this rubber stuff here, when it makes contact with exactly this type of material, it kind of corrodes in some green slime. See here? And if I touch this, see? Nah, I touched the other one, it was, yeah, wet and slimy. What is going on? Nasty. So, but that is not the case here. So it has something to do with this type of metal touching this foam. And we just see these things in old electronics. Different materials are not always compatible. And it shows some 40 years later. Now I better go and assemble everything again. I think I found out about all these things. We have a clearance issue. So I will sand the boards sitting here just a 0.5 millimeter on the side here. And then hopefully I will be able to put everything together here without adding a lot of bend again. And also I found this corner here to be really nasty bent. So that means this one was flying into a trash can or something like that, or somebody dropped it. Look at that. Nasty bend there. And I can easily take this away and straighten this out. I should do that later if I manage to get this thing up and running. To show you a funny thing about installing those cards. If you look at the grooves we have here in each side, so this is the blue card and it goes in here. Of course you can see that will be the power tracks and that will be the data tracks. And if we look at the tracks down here at the bottom of the motherboard down there, we'll see all the data tracks is of course here. So that means this board of course fits in this way. And if we see the connector down there is in the middle. And now I go down and I hit the connector perfectly fine. But what if I am not paying attention to detail and if I flip the board wrong? Of course, look, it fits into the grooves and it slides down and it fits into the connector perfectly fine. And then clickety clickety perfect. What the heck? If they only moved that connector a few millimeters, you couldn't, you can't do these kind of This is dangerous. So I think I'm ready to power this unit. I really want to show you how nice and beautiful it is after my last super cleanup and a little bit of white paint added to all the nasty dents and marks. Of course, I also fixed this side bracket, so now that is nice and straight. And that circuit board here, remember how bad that was with the power supply and all that? I don't want to bend around with those boards. They're full of ICs and all that kind of stuff, and it fits perfectly fine in the socket and all that. So I think I will just leave it as it is, and then let's see what happens. Oh, I forgot. You gotta see the on-off switch. This one, look what happens here. So there's a mechanical indicator in here. See if I see it flips, and then it goes out and go flat. It is amazingly well done. Flippity floppity beautiful. It looks like it's lit, but it's not. Amazing. So now mains is applied, and we are ready to power it up for the first time. So hold your hats. It's using 135 watts, and we got the good power on. And after a little while, it should definitely say 129 watts. I think that is also normal. Why don't you... maybe I should push a button. No? Are we stuck here? I don't know. This is not good. I was hoping for a little bit more than this. How typical is that? I only had to push the right button. So I pushed the frequency, and now it says frequency 1 kilohertz. So what if I put in frequency again? 1 0. So 1 don't work. 444. What? How do I really do this? Hertz. Oh, that's boring. So that is how it works. You put in the frequency in hertz, but what about 1? Okay, 4 works. Oh no, so this super lame membrane keyboard. Ah, that is something. So if 1, 2 and 3 don't work, they are connected in a matrix style. See, this work, this work, this work. See, there's one line that doesn't work. Haha. And this is the back side of the display. And again, this unit keeps amazes me about how service friendly it is. Just 3 screws in each side, and then the whole display pops down. All the wires got nice length, so you can easily take the whole unit out here and poke around with that one. And immediately I see this is the flat cable that goes to the keyboard stuff. That is, of course, a little bit dodgy membrane keyboard down here somewhere, and there's a little socket down here. Oh, damn, this is out of focus. And then there is this keyboard encoder chip. And we got clock, we got display timing, and all those display drivers. So those UCN drivers, this is the 5810s. And here we got the 5815 8-bit latched high voltage vacuum fluorescent drivers. And we got 2 more of the 5810s. And those are, of course, for driving all the digits of the display. Yeah, they're doing everything themselves. I mean, later models, you would buy a ready-made display unit, and then you just interface to that unit. But here they're doing everything themselves. Here's the high voltage supply for the VFD. It says 44 volts and all that. I'm actually quite impressed. So let's try and see if there is a way to pull this apart and get this board out. There was one more thing I find really funny. Look at that little piece of wire here. That's also shielded. Look at that. What is that going to help anybody? But they say, oh, I want shielded cables all the way. Okay, how about this little piece? Yep, I said all the way. So I took away the circuit board here. And this is, of course, the behind the keyboard. I don't understand exactly why we have a big hole here. But look at all the corrosion. So we got some corroded tracks, maybe also a disconnected via somewhere. And it is definitely why the keyboard is not working. Some corrosion here, but how do I service this is my big question. So I somehow need to take this entire keyboard out and then see if I can clean all this and put it back again. I think it's gonna be completely broken, because the way that this works is we got the circuit board and then there is a little riser around this, and you can maybe see the top of the membrane here moves just a tiny little bit, and there's a metal coating on the back side of the plastic, and then it bends down and touches some tracks on the circuit board. So it's probably not possible to fix this without this looking really, really bad. It starts to come off here, so I'm probably gonna push it from the behind, but well, I have nothing that works right here, so it looks perfectly beautiful, but it just don't work. So I'll see if I can fix this somehow. So in the manual, I was able to find the display section quite easily, and I really tried hard to see if I can find any kind of information about the layout and the system of the keyboard itself, but that remained a secret. So somehow the buttons, the switches, the routings, the connector for the keyboard is not revealed. So that means I am a little bit stuck. But let's have a little look at the schematic. We have a little keyboard decoder chip. We got line drivers in and out, tons of logic handling the display signals in and out. And there is another sheet with power supply and high voltage stuff, all the drivers for the VFD, the EEPROM for the characters, and all that kind of stuff. And if we zoom in on the display decoder chip, we see we got quite a lot of X and Y signals going to that connector. So I think that will be my lead. I think I'll try and make a little hand-drawn schematic of how I think it could be. And this way maybe I can figure out which one of the pins is the missing signal. Here is the membrane keyboard. I was able to peel this off real careful. Got still a little bit of sticky. So the back side of that is a thin layer of silver metal, but that is not where we have the problem. The problem is a broken track somewhere here. And you see we got some tracks here at the back, and we got some tracks, some BS, we got some corrosion going on in there. So that is maybe where I should find my problem. I tried to cut away the silicone glue here, and then we got a little double-sided sticky and it seems like it's impossible to poke this free. But at least we got this pin here, and it's numbered, so that should be fairly easy to figure out. And also I got quite a lot of information from the front here. I can follow the tracks. Here we got some visible tracks, and it's of course made in a system so that all those lines here at the top, they're connected together. And then there is one via, and this via goes to the connector, but it also goes to some of the other switches over here. It looks like they're completely different switches, but they are of course also connected in the same matrix system, obviously. So all I need to understand is how this works, because we know this row here, all of this row is not working. And the bottom side, see, we've got vias in all of these. They are connected here and here and here and so on. So that is, those are connected together, and that seems to be working because I can beep a connection from this one to that one and so forth. But here I cannot beep any connections to any of the connector pins. And I tried to scrape my way through the little slime here. And then I'll try and make a little drawing. I think that is the way to do it. Here is what I did. What a fight. Of course, I couldn't find any good information in the manual about that piece of circuit board. So the connections here is a secret mystery. So what I did is I took a photo of this sheet here, and I printed it out on a piece of paper. And also I figured this is the connector, and on the back side here it's actually written, I don't know if you can see this, 1 and 8 and a little 7 down there. So this tells us the pin out orientations and everything for that connector. So this is what I did. We had a little bit too little space in there. So I put this connector out here so it's loud and clear, and that will be the pins of the connector. Okay, so I made some numbers that correlate to the pins. So we got the X and Y connections from the schematic. So we've got all the X's and all the Y's, and this is actually how it is. So X goes this way and Y goes that way. So that is quite convenient for us. So that will be all our X's. So let's take this one. Pin 9 is here, and pin 9 is connected to the top side. So this is my idea. All the top side numbers, the connector got the switch got a top and a bottom side. Okay, so it's quite easy here to see all the top sides here. They're connected together, and then they're also connected to some of the top sides and whatever over here, right? So let's focus on the top sides. This row is not working at all. So there is no top side connection to that one. So we have to figure out how to map everything first, and then figure out the missing. There is a system. 9, 10, 11, ooh, missing 13. Duh, I think number 12 is the missing X line. So that is what I will try and do. I will try and connect that one to that one. But I also have a missing here. I have a missing bottom line. I didn't realize that when I was playing with the instrument, but by mapping and measuring here, I figured out there's also a system here, and here's a little bit weird. 1, 2, 3, what is that? 5, 6. There's a very high chance this is number 4. But in the other cases here, it's 7, 14, and 7, 14, and then 7, 14, 7, 14. and 714. That's just because they don't use that many wires that goes over here in this area. So since this is the same 714 system, I mean, I am very, very sure this is number 4. Just like that. And that will be the numbers I have here. And they go all the way like that, right? 1, 2, 3, 4, 5, 6. We also got some extra switches up here, and they are not mapped to any text at all. And it is like that here, ready for some expansion, or maybe you get a software upgrade for more features, whatever. They are, of course, already connected. And in this area here, we also got some connection or some switches. Oh yeah, they are actually also there in the middle here of the, but nobody knows we got some switches right there. That's what we got. That's quite easy to see right there. So that is what I will try and do. And I think I already figured this out. We got some vias, and I think those vias, they are corroded in the via, because we can really see the problem here with the corrosion. See? You can see here. It is quite corroded. But there is no way I can access the board other than through this hole, because they put this silicone. I mean, no matter how hard I press here, I really tried, it's not gonna give out, it's not gonna get loose. I mean, if I try to do that, I'm gonna break something or get hurt or something. You're gonna get blood all over the place. So I don't want to do that. Let's see if I can figure this out. So I did figure this out. This is the via that goes to that switch. I think is number 4. So that track goes here, and here it is, this track. I cleaned away this double-sided tape, as you can see right here. And under this double-sided tape, tracks start to corrode. And it's, of course, also a problem over here. So, for some reason, this tape has some sort of a solvent or a chemical that is slowly attacking the copper traces. We can even see 2 tracks right there, and this track here is this one that goes to number 4. So I can beep the good connection right here, and then it's lost, and then it's lost. And the 12 is what I know is that row that I need. Unfortunately, this hole here is very small, so I cannot reach this via. So I'm still figuring out how can I repair this missing 12, because it is that via here I need to access. And there is, can I drill a hole in this plastic and not cut any other tracks here? Maybe I should drill a hole here and then solder here on the top. But if I do that, I'm going to have a little blob that sticks up here, and you don't want any kind of height here. So that is also not a good solution. So that is why I am a little bit in pain here about how to fix this. I really want to access this via here from the bottom side. Challenge. Oh, here's what I did. Repaired this little track here, added a little wire. I ended up drilling a tiny little 0.5 hole right there and soldered in this tiny little wire. I hope I made it super flat so it will still work. And then I cleaned all the contacts a little bit. Now I really hope it's gonna work. I think I will share the disappointment or the joy together with the video. So let's turn it on, and now it's doing the self-test and all that. And I think it actually is waiting for a button, and it must be the frequency button. So now let's try 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so far so good. All my buttons seems to be working. And then, okay, that is error. Okay, let's say 1, 2, 3, 4, 5, 6 kilohertz. That should be 1, 2, 3 kilohertz, like that, right? So how do I enable output? I still haven't read the entire manual, but I think it is this output here. Output off, load out 2. So maybe I push 2 and then output. How do I enable on amplitude? 1 volt. Damn it, I need to read the damn manual to get output. Oh no! And I got output. I mean, I finally figured this out. It is insanely difficult to use, but of course you should read the goddamn manual. And I am totally too lazy for that. So let's go function. Okay, so 1 function triangle is what it says. What if I say 0 function sine wave, and then nothing happens? You have to hit execute, and then you get the sine wave. It is that simple. So there's an offset. Okay, let's go offset. Offset 1 volt. 0 offset, execute, and there you have it. So all there is to it is just to understand how it works. I am super happy about that. So what we got is 9.9 kilohertz. Oh no, that cannot be. It says it is 10 kilohertz. What if I say 100? 1, 2, 3, and then say frequency. It says 100 kilohertz, and then hit execute, and then we dial here. Okay, there's something wrong with the time base. It says 99.3 kilohertz, but it is pretty close. Oh, you can even see it's digital. Look at that. It is definitely digital. You can see it. This is normally not visible with those bits and stuff here. On this scope it's 10-bit scope, so it's really not visible. But it works. I don't understand exactly. It says frequency and then AM and what? I don't know. There's probably a frequency offset or frequency something. But now I will play with this for the next few days and finally figure out how to program it and use it and all that. But I really think this is all I wanted to show in this video. That I was able to repair it and what it consists of. And it's just crazy complex, definitely. And it's using 128 watts. So that is nice too. But anyway, thank you very much for watching. Bye bye.